Hello, everyone. Welcome to this presentation. My name is Albert Akuno from the Centro de Investigación en Matemáticas in Guanajuato, Mexico. I'm a PhD student there, undertaking my studies in the field of probability and statistics. My advisor is Dr. Leticia Ramirez, and my presentation is titled Bayesian Inference and Uncertainty Quantification of Multi-patched epidemic models with partial mobility, residency, and demography. So welcome to the presentation. I'm going to give a brief introduction of some epidemic models, simple epidemic models, so that you can be able to see where we are coming from and where we are going to. The models that, or the mechanics or the dynamics that we are going to consider in the construction of our model, which is our proposed model. Then thereafter, I'm going to give a brief. I'm just going to rush over the mathematical properties of the model that we will have proposed, and then go straight away to uncertainty quantification. Because mathematical properties of the model is not the import of this presentation. Now, what is important in this presentation is uncertainty quantification. So it is important to mention that this research or this work is at the initial stages of, and what we have done is that we are trying to look at what works and what is the best path that we can be able to take, what gives us reasonable results. We are still in the initial stages of the research. What we have done extensively so far is the mathematical properties of the model, and that is in the branch of pure mathematics. It's not really in statistics. So the uncertainty quantification bit is just still in the informative or the formative stage, I should say. This work is more, of course, as I've said, the main objective of the research is to propose a deterministic epidemic model, and then, with population mobility, and then perform uncertainty quantification on it, which entails estimating the parameters given observed data, estimate the parameters of the model, ideally do what we call inverse problem. This work is an ongoing work, as I've said, with the collaboration of Dr. Tan Bui Tan and his student Chahak from the University of Texas in the United States. So just a brief introduction of the compartment models. They were introduced by Kerman and McKendrick in 1927. And basically, they are models that divide the population. If you can consider, if you have a country or maybe an environment, you have a population, those who are susceptible to the disease, and those who, after being susceptible, they come in contact with the infected individuals at the initial stage, and then they become infectious, and then after becoming infectious, they recover after a given period of time. The rate at which the susceptible get into contact with the infected individuals, initially infected individuals, is beta. Then the infected individuals recover at a rate gamma. So you can imagine this type of dynamics, which is governed by different set of differential equations, 1.1. And the differential equations, like the first one, which is the most important one in this case, is the infection dynamics, the rate at which, the rate at which the susceptible individuals come in contact with the infected individuals, and then they become infectious at this point. After they become infectious, they go to, when they become infectious, they go to the infected compartment, and then they recover after some time, in which case they are now removed from the infectious compartment. In this case, the population is, we have a constant population. We are assuming that the population is closed. There is no introduction of any type, introduction of any individual. There is no recruitment. There are no leakages. There are no deaths in this case. So this one is the famous, it's SIR model, and it's in this case just for a single patch. What we are trying to do is to build a model using this type of dynamics or this type of intuition in a multi-patch environment where we have several cities or several environments, and this type of dynamic happens in each and every city. And then these cities are connected by some sense of mobility between them. So in this case, this is just for a single patch case. And it is important to also mention that such models can also be extended. Since the introduction, there has been a lot of research that has gone on that has led to extension of such models. And the extension, as you can see, it's a simple model that maybe may not be able to, if you consider it, you may not be able to model so much what happens in a real life scenario, in a real life problem or real life infection dynamics. And so you can be able to extend it by including other realistic compartments. Like, for example, in this case, we can include the exposed compartment. Like in COVID, we are told there are those who are asymptomatic to the disease. That means that when you get exposed to the disease, the susceptibles get exposed to the disease is in them, but it is not shared already. It's in them, they are not showing any symptoms, they're just okay. And in that case, they are in the exposed compartment. After some time, the disease is shared. That means that they start showing symptoms and they can be able to infect other individuals who come in contact with them. And in that case, they go to the infectious compartment. And the rate at which they go to the infectious compartment is the rate sigma, and then they recover at a rate gamma. The infected recover at a rate gamma. So this one again is just an extension. The dynamics remain the same, and we are assuming that the population is closed. There is no recruitment of any nature. There are no leakages. There are no deaths. In this case, we assume that the disease is friendly. I mean, you simply are infected, and then you stay infected for some time. You are exposed, you are infected, you're infectious, and then you recover. And then that's it. There are no deaths, there are no recruitment in this case. But again, we can consider a case whereby we have recruitments and we have deaths. In that case, we are saying that the susceptibles are being recruited at some rate, lambda in this case, and then in each and every epidemiological status that is susceptible, infectious, recovered, they die at some rate mu. The dynamics in this case, we have this where after the individuals recover, they become susceptible again at some rate tau, so they lose immunity. This is a type of disease that confers partial immunity. In the previous cases, that is type of disease that confers permanent immunity, in which case they recover and that's it. They are not, they cannot be infected by the disease once again. But in this case, this is a type of disease that confers partial immunity, in which case after they have recovered, they become they become susceptible once again. So this is the case of SIR model, which is governed by this type of differential equations 1.3. And it is important to notice that in this case, the population size is not constant. It varies. The population size varies with time. So this is the case of SIR. We have the same case for the susceptible. For the exposed, SEIR. We have exposed individuals here. They die at some rate mu. We have introduced another compartment, but once the infectious individuals recover, they go back to being susceptible. Then we have this set of differential equations that govern this. So all this that I have been able to show right now, they are just happening. This dynamic is happening in a single environment. You can imagine in a single environment or in some city, this dynamic is happening. But now what happens when you say, for example, you have different environments. You have one city A, city B, city C, city D, and which this type of dynamic happens in each and every city. And then these cities are connected by mobility. Of course, individuals, we are not living in an island. People move from one environment to another. So when individuals move from one city to another, what happens in that case to the disease dynamics? That is what we are interested in. And we have used this type of model, the SEIR, to come up with a multi-patch model that models or that captures mobility and residence time. That means that individuals move from one environment to another and then they take some time there before they come back to their population. So our interest is to study what really happens to the disease dynamics or the infection dynamics in that case. We come in to extend some work that was done by Bichara and others in 2015. What they did, what Bichara and others did in 2015 is that they considered a model, an SIS model with multiple subpopulations, that is patches, we can call them cities, and with some possible transmission rates, the PIJ. In this case, the PIJ in this case is the time that these individuals move. When they move from their environment, they take the time that they take in the other environment that they have moved to. The pitfall or the gap that existed in this work by Bichara is that they assumed that this PIJ or this parameter here, it was like coupled to mean that it's a proportion of individuals move, a proportion of individuals move from one environment to another, and then they take the same amount of time in that environment that they have moved to. So in that kind of setting, this parameter here was modeling or coupled to two instances. The first instance is the proportion of individuals that move, and also the time that they take when they move to that other environment. But really, it is not realistic to assume that I mean, everybody can be able to move from one environment to another. That is what was inherent in the assumption. And also, it is also not realistic to assume that when they move, when everybody moves, then they take the same amount of time in the environment that they have moved to. And so we come in by introducing a mobility parameter, in which case we say now, we decouple this into two. We say that now let's say that we have a proportion of individuals that can move from one environment to another. When this proportion of individuals move to another environment, then they take a proportion of their time in that environment that they have moved to before they come back to their environment. So we come in and introduce this mobility parameter. We call it alpha I, which denotes the proportion of individuals that move from patch I to any other patch J, and then once they move, they take Pij of their time, which is between 0 and 1 of their time in the other patch that they move to, and in that sense, we can be able to see that those who are in the cruising mode at any given time, we are going to have an average of this number of individuals, that is alpha I times Ni times Pij in the environment that in the jth or in the jth environment or in the jth patch. And then these guys are going to remain 1 minus alpha I. Of course, when alpha I move, 1 minus alpha I remains. So these are the guys that have remained in patch I. At any given time, you are going to have this type of this proportion of in the residents in patch J and in patch I. These are the parameters that we have considered. As I've mentioned, alpha I is the proportion of individuals that travel from patch I to any other patch J, and then the rest are self-explanatory, as you can be able to read from this. We have the rate of recruitment for patch I, the rate of contact, the contact rate, the death rate, the recovery rate, the rate at which the individuals lose immunity, and the rate of disease-induced mortality, and then there's the rate at which the exposed the individuals become infectious. So all this happens in patch I. Putting all this information together, we have this type of dynamics, of which ideally every other part remains the same. What differs is the infection dynamics here. What happens when the susceptibles of patch I come into contact with those who remain in their patch and those who move to other patches. So this first part here is the rate at which, or is the proportion of susceptible individuals of patch I who have been infected, those who remain in patch I. And then these are the susceptible individuals of patch I being infected by infectious individuals, infected individuals, when they come into contact with infected individuals from other patches. So these are infection of susceptible individuals who remain in patch I. These are infection of susceptible individuals of patch I who move to, by infected individuals who move into into patch J. So the other dynamics remains the same: the death rate, the rate at which the susceptibles die, the rate at which the recovered lose immunity and become susceptible. So every other dynamic remains the same as in the single patch case. It's only that in this case, we're now considering multiple patches. Once we have this model, the main import or the importance, the main idea about this, this work that we want to do is we want to see now, given the infection data, let's say you have daily data, daily positive cases of infection, then can we be able to estimate these parameters, any of the parameters here? Like in our study, we have considered estimating beta, we have considered estimating gamma and kappa for each and every patch. And that is what is called an inverse problem, uncertainty quantification, or inference on this model. And we're going to do the estimation using Bayesian method. But before then, this model can be written in a more compact form. As you look at it, it looks a little bit scary, but we can write it in a compact form or a matrix form, and we can use matrix theory to be able to analyze this. So 2.2 is an equivalent model of 2.1, but in this case, this one is in matrix form, and we can be able to use matrix theory to be able to analyze some of the properties of this model. There are also even other computational methods or OD integration methods that can be used to solve matrix models of this nature. And an important threshold in epidemiology is what we call the basic reduction number. It is computed using the next generation approach. I'm not really going to go into the details of the next generation approach of computing the basic reduction number. At this point, I'm only going to describe or to define what the basic reduction number is. The basic reduction number in a layman's language is the number of secondary infections that are generated by a primary infected individual introduced in a fully susceptible population in the entire time of infectiousness of this primary infected individual. So you can think of it in this way. In a population, you have a fully susceptible population, you introduce one single infected individual, then you ask yourself, in the entire life of this infected individual that you have introduced in the environment, what is the number of secondary infections that this person is going to generate? So the number of secondary infections that the primary individual is going to generate, that is what is called the basic reduction number, and is very important in epidemiology. Virtually all analyses are based on this threshold, which is very, very important. In fact, we say, I believe you have heard that when the basic reduction number is greater than 1, then we say that there is an outbreak of the disease, and when the basic reduction number is less than 1, then we say that the disease is under control. So this threshold, the basic reduction number, is very important. In this case, this is the global basic reduction number for all the patches in the presence of mobility. And we have the basic reduction number in the absence of mobility. That means that the environments are not connected in any way. This is the basic reduction number for patch I in the case when there is no mobility. That is 2.4, and then 2.5 is the basic reproduction number that we have for patch I when in the presence of mobility. So it is very important to look at what some of the properties of this or the infection dynamics based on this basic or these threshold quantities, the basic reproduction number. We also do some small mathematical analysis of the model, and we found out that the global basic reduction number is bounded by the minimum and the maximum of the basic reduction number in the case when the patches are independent. That means that when they are not connected in any way, based on these assumptions that the demographics or these parameters are constant, save for the infection parameter, which remains, which varies, right, which changes over time, which is not constant, I mean. Another important bit of such analysis is the global stability analysis, of the disease-free equilibrium and the endemic equilibrium. The disease-free equilibrium is just that the state at which we don't have the disease in the system. And the endemic equilibrium is when we have the disease in the system. That means that there are some infected individuals in the system. In that case, for us to do such global analysis, it is important for our model, we found it easier to have an asymptotic version of the model that we have looked at so far. And the asymptotic model is obtained by replacing the total population by this quantity that we have here, that is the recruitment rate divided by the death rate. So this system here will help us to be able to understand the global properties of this of our system, of our model, and this is the corresponding basic production number. One thing that it is important to mention is that when you have an epidemiological model, especially the one that is dealing with the population, in this case, you need to find out whether it is well posed. And for it to be well posed, you need to, I mean, of course, you know that when you have positive initial conditions, then the solution of that model will be positive, because in this case, we are dealing with mobility. I mean, we are typically dealing with population, in which case, for it to be biologically sensible, then we have to have it as the solutions as being positive. So this theorem tells us that the given initial positive conditions, the solution of our model or the compartments will be positive, and they will have, the solution will be unique, that continuously changes with changes in the data. In that case, we now conclude combined with, so this theory, this one here, I mean, this theorem here, combined with the fact that our system is locally Lipschitz, it means that it has a unique solution, and that brings us to conclude that the model is biologically well posed. Also, we have shown that the model has a stable disease-free equilibrium when the basic production number is less than 1, and it is unstable when the basic production number is greater than 1. We have also shown that the system has a unique endemic equilibrium, which is attractive, and that that endemic equilibrium is locally asymptotically stable. We have not been able to show global asymptotic stability, but we have been able to show local asymptotic stability of the endemic equilibrium point. I mean, this not being the import of this presentation, I've just brushed over the mathematical properties. What is important at this point is really Bayesian inference. Now, as I've said, inference is just, we want to, given you have observed data, then you want to learn the trajectories of the parameters of the model when you have observed data. And that is Bayesian inference is very important in that case. And Bayesian, in terms of learning these trajectories, we use, there are developed tools that have been used, the Monte Carlo Markov chain. This Monte Carlo Markov chain have solved some a very old problem that has been there of in the posterior distribution. When you solve the target distribution that you want to solve, or that you want, whose parameters you want to solve or you want to sample from, is always intractable. That when you use it in a real life scenario, real life phenomena, most of the distributions that characterized in real life scenario are intractable, in which case they are complex and we are not able to find the integration of their normalizing constant. So the MCMC tried to solve this problem, but the MCMC is plagued by some challenges. They are, non-convergence, in which case, when you start, when you get the chains, they do not converge to in some cases. Of course, when you're dealing with complex models, it's sometimes you don't achieve convergence of the parameters of the samples to the target distribution. Also, we know the MCMC, the current sample point depends on the previous sample point, and in that case, we have very high correlation that exists between these sample points. So, and they are also very slow. They can be very slow. The MCMC can be very slow when used in large scale data and in complex posterior models. And it is for this reason that we have chosen to use the Stein variational gradient. The Stein variational gradient descent was introduced by Liu and Wang in 2016. And in a nutshell, it's a model, it's an algorithm that has some desirable properties or some desirable advantages over the MCMC in that it is efficient. Its efficiency is achieved from the fact that it tries to approximate a simple, just a moment, it tries to approximate a simple, the target distribution using a simple, using a simple prior distribution. So in that case, it minimizes the Kullback-Leibler divergence of these distributions. Kullback-Leibler divergence is just a divergence measure of the distance between two distributions. So SVGD tries to minimize the distance between the prior distribution and the target distribution so that it transports the samples, the initial samples. When you begin with an initial sample, it transports the initial sample to the target distribution by minimizing the distance between these two distributions. And this SVGD can be applied in large scale setting. It can be easy to apply it in large scale setting. And the algorithm samples from the highest probability density of the target distribution. Of course, it transports the initial distribution or the initial samples into the highest probability density area of the target distribution. So it is important in this case. Basically, it minimizes the distance between these two distributions, these 2 points, the 2 sample points from the 2 distributions by minimizing the distance between them. And it does so by looking at the direction of the steepest descent, or the direction of the steepest gradient, right? And it takes the negative of that to reach the global minimum point. So basically, what it does is that we have a transformation of this nature. Of course, this one here I've just explained that we are trying to minimize the distance. You consider, say for example, we have Q, whereas the initial density we are trying to use to approximate the density, the target density P. So we are trying to minimize the distance between them, what we call the Kullback-Leibler divergence. And with the Kullback-Leibler divergence is just the expectation of the log of the ratio of Q and P. And we have a one-to-one transformation of this form. And then what we are interested in is to estimate this quantity here, this phi. So this psi here is just a smooth function that represents the direction of the perturbation, the direction of the descent, the direction of the gradient descent. And we try to estimate it in such a way that we find that direction that maximizes the negative, gradient. And then we update this transformation at each iteration that we run the algorithm. I'm going to show you the algorithm in a bit, but basically that is the general idea behind SVGD. In that this is how it works. This is just some theory about it, but basically how it works is in this algorithm that we can find in Liu and Wang in 2016. What happens is that we start with target distribution, and then we go to we start with an initial distribution from the an initial sample from our, we call it initial particles from our initial distribution. And then we try to transport, to update at each and every stage, at each and every iteration, we update this initial sample to the target distribution using empirically observed observations at each iteration using this quantity here. This quantity here, as you saw earlier, it is that it is that direction, or is that quantity that maximizes the gradient the direction of the descent that maximizes the negative gradient in this case. You see this quantity that we have here, it is approximated, it is estimated, the optimal value is estimated as this, which is simply the expectation of the log, or the gradient of the log of the target plus the gradient of the kernel function. This kernel function here is we use an RBF, and so what we are interested in is just to reduce the distance between the observed or these samples. This distance here is what we are trying to reduce, so that we transport our initial sample to the target distribution. So this quantity here, this one here that we are trying to estimate, that we estimate it by getting the mean of what we have generated, or the mean of the samples values that we have generated. This n here is the total number of samples, or the total number of particles that we have generated at each and every iteration of this algorithm. And then we get the mean, and then we approximate our sample, this transformation, using that empirical. So we are going to replace this by psi star. And then in each iteration, we get the value of this transformation. In that case, we are going to get our target distribution, or we are going to transport the initial distribution that we get from Q. We transport it to the target distribution, and we say that after some time, our initial distribution become the same as the target distribution, so that we get our samples, and that happens in this algorithm. So what we have done, we are not saying this is not our algorithm, we are just applying it to our model. And for us to be able to apply it, we need this distribution here, that is the target distribution, or the posterior distribution, so to speak. The posterior distribution is built in our setting. It is built as follows. We consider the observed positive cases in each and every patch, which is Y in this case. Let it denote from 1 to n. Let it denote the observed data from the n patches. And then we have the theta, capital theta here, which denotes the number of parameters that we want to estimate. When we put this number of, when we combine these observations together, that is the observed data from each and every patch, given the parameters that we want to estimate, and then we find the product. We get what we call the likelihood function. Once we have the likelihood function of the observed data, given the parameters that we want to estimate, we for each and every patch, then we get the product of this likelihood function for each and every patch to get now the combined likelihood, that is the likelihood for the data, the observed data from all the environments. And then once we have the combined data from all the environments, we need to be able to construct the posterior distribution, we need the prior distribution. So the prior distribution, we assume, we say if we have, say for example, mi number of parameters to be estimated, then we need to assume that each parameter follow some distribution, and then to get the combined prior distribution for all the patches, we simply get the product of the prior distributions of each and every parameter in this case, so that we get by 4.2. So we have the likelihood, we have the prior distribution, then we use the likelihood and the prior distribution to build the posterior distribution, what we call the target distribution in the SVGD in this manner, by simply getting the weighted average between the likelihood and the prior distribution. This quantity here is what we call the normalizing constant. It is what brings about the intractability of the posterior distribution when applied to, of course, real life scenario or real life data or epidemiological modeling. And so SVGD comes in handy because it handles this intractability very efficiently. That's why at the end of it all, we construct our posterior distribution in such a way that we only take the proportional part, the part that is proportional, the part that is dependent on our parameters that we are trying to estimate. So we are just going to say that this target distribution is proportional to the numerator that we have, the numerator quantity that we have up here. In our setting, we are trying to estimate beta, with kappa and gamma. And of course, we are doing it in a two-patch case. But before we go to the two-patch case, this is just the general, constructing the posterior distribution for the general case. Again, we assume that each of the observed data follows a Poisson distribution with mean of the infected compartment from the simulated or from the SEIR model. And then after assuming that, then we get our likelihood in this manner. When we assume a Poisson distribution, 4.4 will be our likelihood. It is important to note that we can as well assume that our observed data follows a different type of distribution, say, for example, a normal distribution or a negative binomial distribution. This is a negative binomial distribution is very important in measuring our dispersion. Of course, epidemiological data or count data is characterized by a lot of variability in them. So it is also important to be able to try to estimate that over dispersion of that variability. That can be done using negative binomial distribution. So we are also thinking of going that direction, or maybe using a normal distribution to see how different our results will be from when we use a Poisson. We assume that the observed data follows a Poisson distribution. So we have our likelihood. Once we have our likelihood, this is the likelihood for each and every patch. Then to get the likelihood for the whole environment, for the whole n patches, the combined patches, we simply find the product, which is given by 4.5. And then we assume, for our case, we assume that each parameter follows a prior distribution, gamma 1, prior distribution. And once as we assume that, then we are going to get our target distribution by simply getting the product of the likelihood and the prior distribution. I had already mentioned how we construct this prior distribution previously in the previous slides. So we have 4.6 in that case. For the two-patch case, putting all that information together for the general case, it's just for the two-patch case, we have 4.7 as our target distribution. Once we have this for the two-patch case, this is what we feed as we take as our target distribution in SVGD, and this is the sample or the distribution that we sample from. When we sample from this, with the intention of measuring beta, kappa, and gamma, you may ask yourself where are these parameters that we are measuring. They come into this equation from these observations, the I1 and I2. So I1 will carry kappa 1, will carry beta 1, kappa 1, and gamma 1. I2 will carry beta 2, kappa 2, and gamma 2. So they come from the system, from the model themselves. And so we want to estimate those parameters and using SVGD. So when we apply that, what we do is that since we have not been, we are just in the initial stages of our analysis, we assumed, we just generated some synthetic infection data onto which we added some noise, and then we tried to estimate and see if we can be able to get these parameters that we have, that we use to simulate them. So what we have done is that we have used these parameters to be able to estimate synthetic data, in synthetic infection data. Once we have simulate this in synthetic infection data, then we use SVGD to be able to estimate the parameters from, after adding some noise to this synthetic infection data, then we try to estimate these parameters and see if we can get any values nearer or equal to these parameters that we are trying to estimate in this case. So we use these parameters to be able to estimate, to simulate the synthetic data. These are the data that we simulated, the continuous, the dashed curves are the ones that have been simulated from the system, and then the dots are the ones that are the observed data that we have by adding some noise onto the simulated infection data. So these are infection data that we have simulated and the ones that we have observed by adding some noise onto them. So when we apply SVGD, we get these samples for beta 1, beta 2, In this case, we have gamma 1, gamma 2, kappa 1, and kappa 2. These are the estimates, or the estimated samples. They are posterior samples that we have obtained from the target distribution. We have obtained them from the target distribution. They appear, well, they are not perfect, because if you look at it, look, for example, beta 1. The beta 1 that we used, look, beta 1 and beta 2 that we used to simulate the synthetic data was 2.2 and 1.5. But when you look at the mean of this, 2.2 is somewhere here, 1.5 is somewhere here. They are more or less to the left, and so we cannot claim confidently that the mean of this data that we have will be 2.2 and this one will be 1.5. A little bit to the left. So that's why I'm saying the samples that we have obtained are not perfect, but we have reason to believe that we are on the right path. With some tuning here and there, we can be able to improve these observations that we have, or we can be able to improve this estimation. But nevertheless, this is what we have at the moment. And as I mentioned, the work is still ongoing, and we believe that we'll be able to get very good estimation or very good sample points that correspond, whose mean, of course, correspond to the real values that were used to simulate the data. So those are the ones that we have for gamma 1, gamma 2, kappa 1, kappa 2, which are also not very close. Not very close to the real ones that were used, but we, as I've said, we have reason to believe that we are on the right path, and so we are going through some tuning and some improvement here and there to be able to get the true, the real data, or the real estimated, a good estimation, or good estimation samples. This is what we have, the curves that we have when we use the estimated data to plot the curves. As you can see, the estimated ones, when we plot them, they are a little bit skewed. They are a little bit to the left of the observed data. That's because, as I said, our estimation is not perfect. It's not very good. So that's why in a scenario where they are good and they correspond to the real ones, then when we plot these curves using the estimated parameters, they should be overlined, at least overlined or in line with the observed data. But in this case, they are not, a little bit to the left. And so with some work that we're going to put in place, we believe that we are going to shift them so that they can be, the simulated data using the estimated parameters are going to be in line with the observed data. So that is all that we have done up to this point. We believe that as time goes, over some time, we are going to have this work will be complete with very good results. Thank you for your time. These are some of the references that I have. Thank you for your time, and thank you for listening to the presentation. I hope that it will be helpful and it will inform some policy formulation, at least in the field of epidemiology. Thank you.